Hello, we're Voxel, and we've created a 3D holographic persistence of vision display. My name's Andrew Hellerbull, and my partners are Anna Caro, Marcus Chan, Ryan Chen, and Akash Harpanahali. Let me introduce you to Voxel, the world's first fully volumetric holographic persistence of vision display. What you see here is a holographic Utah teapot, which is somewhat known as the hello world of computer graphics. So what exactly is persistence of vision, also known as POV? Well, POV is the phenomenon where an image is retained in your retina for a short period of time even after light rays have stopped entering the eye. Using the POV phenomena, displays can be designed by rotating and updating LEDs fast enough so that the blended together light forms an image. Typically around 15 revolutions per second is needed for these displays to achieve persistence of vision. There are three common topologies of displays as seen below. The 2D fan topology, which can achieve high 2D resolution but is only viewable from one direction. The globe topology, which can also achieve high resolutions but is simply a 2D image wrapped around a sphere. And the stacked blades topology, which achieves true 3D in lower resolution and can't display pixels in the middle cylinder of the display. However, Voxel is different. It surpasses all of these limitations by creating a full grid of LEDs that is rotated quickly enough to allow for fully volumetric displays. The higher volumetric pixel density allows for high resolution photos, higher than any other POV display available. There's also software support for full 3D animations as is seen below.
Seeing as there have been no previous attempts, Voxel aims to assess the viability of 3D POV displays compared to other lower dimensional holographic technologies. With this work, Voxel has the potential for commercial use in advertising, entertainment, and data visualization, and as such, will be open source to spur future development in 3D POV displays. The 2D display panel has a 48 by 30 resolution and a 5.4 kHz update frequency. The 2D panel rotates at 15 rotations per second and updates every 1 degree to achieve an overall refresh rate of 7.8 million LED updates per second.
To compete with other holographic displays on the market, we need at least 10 times more volumetric pixel density than other POV displays. Voxel achieves this and exceeds it by having 25 times more pixel density than other POV displays. Another functionality is to be able to display different colors on our volumetric display. And Voxel has 65,536 unique colors that can be displayed on a frame. In order to achieve the persistence of vision, based on the speed that the human eye and brain can process an image and retain the image, we calculated that the display needed at least 12 frames per second in order to achieve persistence of vision and create the illusion of continuity. On our display, we can update at 15 Hz or higher and has been tested to prove persistence of vision. We also designed for Voxel to be manufacturable at a reasonable cost at quantity that matches other competitors in our market, of about $1,500 at scale. With a simple script, you can simply drag and drop a 3D model downloaded from Thingiverse or even a 3D animation generated using popular 3D software such as Blender. The script will automatically convert your file into a point cloud, which will then be sent to MATLAB to be converted into our custom .vox file format. A Raspberry Pi then takes the .vox file and sends the data over HDMI to an FPGA that decodes the file format to update our LED matrix.
Voxel is the first ever 3D display to support any arbitrary mesh file with high resolution, including standard .stl and obj files. Here's an example of the pipeline that creates a hologram. The original teapot STL file is randomly sampled to generate a high-density point cloud. This point cloud is then resampled with some tolerance at the individual points in our cylinder to generate our unique 3D mapping, pictured on the bottom left. The bottom right is a picture of Voxel actually displaying this mapping, creating a hologram. Voxel takes this one step further through its ability to display arbitrary 3D videos. Animations in Blender are exported as a series of mesh files, which are simply compiled into a series of frames at a desired frame rate. The resulting effect is very unique. Voxel is the only truly 3D display capable of outputting high-resolution 3D holographic video. There does not exist any lossless 3D video format, so we decided to make our own. The .vox file format can store 3D video data for any spinning LED array of any arbitrary size. It achieves a compression ratio of about 6:1 with normal usage, and supports videos and stills. The format can easily interface with any language, and we have created examples for outputting .vox files from MATLAB, C, and Python.
Once a .vox file has been generated, it needs to be sent to the LED matrix. This is accomplished by first sending it to a Raspberry Pi, which can use a custom encoding standard to send the data over HDMI. The FPGA receives the HDMI data in a continuous stream and uploads it to SDRAM. Then, the LED matrix can periodically pull that data from SDRAM so that it can update the LED matrix. We'd like to acknowledge the many people who have helped us throughout this project. First, we'd like to thank our advisor, Kyle Bryan, for all of his support. Second, we'd like to thank Dan Foisey, the creator of Flickr, for lots of technical assistance along the way. And we'd also like to thank the senior design team, including James Steinberg, Kevin Ferry, and Dr. Fraser. And finally, we would like to thank Mark Easley from Texas Instruments for generously donating LED drivers for our project. We'd also like to thank our sponsors, the Georgia Tech School of Electrical and Computer Engineering and Texas Instruments.